Good day. For those of you who do not know us, we're the instructional staff for ECE 150, Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to describe the ternary or conditional operator. So in this topic, we will review conditional statements and then describe the conditional operator, although it's usually just called the ternary operator. We'll look at some examples and recommend the use of comments and parentheses. Now, to date, we have seen unary and binary operators, that is, operators that take either one or two operands respectively. The conditional operator, however, takes three operands, and we'll see quickly how that's done. However, because it is the only operator to take three operands, it is often just referred to as the ternary operator. Now, we have seen conditional statements, but both the consequent and alternative bodies must be separate statements. Okay, not bad. We've used this up until now. So the format of the ternary operator is as follows. We have a condition. Just like a conditional statement has a condition, we can place a condition in the first operand. The first and second operands are separated by a question mark, and the second operand is a consequent expression. It can be any appropriate expression that you're looking for. So the consequent expression is then followed by a colon, which is followed by the alternative expression. So if the condition evaluates to true, the entire operator evaluates to the consequent expression, whatever it is. However, otherwise, if the condition is false, the entire expression evaluates to the alternative expression. So basically, we can use the ternary operator if we only need a single expression or to choose between one of two possible expressions. We're going to look at a few examples. For example, we could simplify the absolute value function significantly because the return statement returns an algebraic expression. In this case, it's going to return one of two expressions. We have a condition, x greater than or equal to 0. If that is true, then we will return x, because the entire conditional operator will evaluate to the consequent expression x. If, however, x greater than or equal to 0 is false, then the entire expression evaluates to the alternative expression, which is negative x. And so if x is negative 17, then the condition is false, and the entire expression evaluates to a negated negative 17, which is positive 17. Here's the sinc function, which is defined as sine of x over x unless x is equal to 0, in which case sine of x over x is 0 over 0, which is indeterminate. But if you take the limits, sine of x over x as x approaches 0 is 1. So, if x is a non-zero value, this expression evaluates to sine of x over x. If x is equal to 0, then x not equal to 0 is false, in which case the entire conditional operator evaluates to the alternative expression, which in this case is just 1.0. To see how this may be used in an arithmetic expression, here I query the user for two values, x and y. What I'm going to do is calculate the absolute value of x minus y. So when I calculate diff, I first here have a conditional operator that calculates the maximum of x and y. If x is greater than or equal to y, this evaluates to x. Otherwise, y is greater than x, in which case the entire expression evaluates to y. from whatever that evaluates to, I subtract off this expression. Here, if x is less than or equal to y, this evaluates to x. Otherwise, x is greater than y, in which case y is less than x, so this evaluates to y. So essentially I have an algebraic expression here that calculates the maximum of x and y and subtracts from that the minimum of x and y. This is one way of calculating the absolute value of x minus y. And that is what would be printed to the screen if you were to execute this program. Now, suppose I'd like to convert a double to an int. Normally, if I assign to an integer a double value, what will happen is that the fractional component of the double will be truncated and the integer component will be assigned to the integer. However, if x is greater than the largest possible value of an integer, then the behavior is odd, and I'd actually have to look it up. It's not what you'd expect. So what I'm going to do here instead is I'm going to assign to n a result, but first I'm going to check if x is greater than or equal to the maximum possible value an integer can take. I will just assign n the maximum value n can take. Otherwise, I will assign to n the value of x. Okay, that should work, because now if I execute this program and I am asked to enter a positive real and I enter 3.14, then it's just going to print out the value 3. However, if I run the program again and I enter this number, which is greater than the largest possible integer value, then n will be assigned the maximum possible value that an integer or an unsigned integer can hold, which is 2 to the 32 minus 1. Now, in the previous slide, I hard-coded the value 2 to the 32 minus 1, because after all, I calculated that using Maple and it was easy enough. But you don't have to do these calculations yourself. Instead, you can use the limits library. So for example, while the notation may be a little bit awkward here, we haven't covered templates. If you put the type inside the angled brackets and ask for the minimum, this will evaluate to the numeric integer value that is the minimum that an int can store. Similarly, this will evaluate to the maximum an int can store. This will be the minimum that an unsigned int can store, which is 0, and this is the maximum an unsigned int can store, which is of course 2 to the 32 minus 1. So if I was to compile and execute this program, the output would be the values we expect. 2 to the 31, negative 2 to the 31, positive 2 to the 31 minus 1, 0, and 2 to the 32 minus 1. This way, you don't have to remember what these values are and you don't have to recalculate them. So here's an example where you could have or avoid a division by 0 error, which would actually terminate your program. In this case, we query the user for 2 non-negative integers. Consequently, the denominator may still be 0. So if the denominator is 0, then we will set result or initialize result with a value of the maximum possible unsigned integer. Otherwise, we will simply evaluate m divided by n, and we'll print that result, whatever it is. Now, the appearance of the conditional operator is not natural for most programmers, and therefore it's really beneficial to comment any use of the conditional operator, especially if it's more complex than a simple evaluation of just one statement with a reasonably straightforward condition. If any of the operands are more complex than a local variable parameter function call or literal, or a unary operator with one of these as the operand, then put parentheses around those operands. As you may have seen, every single time I've used the unary operator in these talks, the condition is always surrounded by parentheses. It just makes it clearer for the reader of the code to understand what is going on. Yes, you may not need them, because after all, the precedence of the unary operator is actually quite low. But for clarity, add those parentheses, make it clear what your intention is. If the conditional operator is being used in an algebraic or logical expression, so it's actually only one part of a larger expression, then put parentheses around the entire operator and its operands. If, however, it's just the right-hand side of an assignment, or what's being returned from a function, the parentheses aren't that necessary. So, in this lesson, you now understand the C++ conditional or ternary operator. You know how to use it, and you know you should be a little bit careful when you are using it. Make sure you make use of comments and parentheses to make your intentions clear. However, if you are using it, it can make your code appear much simpler. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!